This video is going to review how we solved the Schrodinger equation for the eigenfunctions and the energy levels for the rigid rotor, as well as the other various operators that commute with total energy operator for the rigid rotor. So to start, we do the same thing we always do that we've done for the particle in the box and for the harmonic oscillator, and we simply solve the Schrodinger equation. Now, the Schrodinger equation might look a little bit different from the last time you saw it, and that's because of two things. One, when we have rotation in 3 dimensions, so we have to consider the 3-dimensional variables. And two, for rotation, it's obviously easier to consider rotation in terms of these angles theta and phi rather than the Cartesian coordinates x, y, and z. So we've made changes to a coordinate system that are reflected in the changes of the second derivatives. But what's going on in the brackets there is just the same d2 si dx2 that we've seen extended to 3 dimensions and then changed to spherical coordinates. Now, for our bond rotation, we are going to assume that our molecule is rigid, that the bond distance isn't changing. Now, in the last video, we talked about vibration and changes in bond length. So we know that's not true, but we're going to assume it here for these purposes. And we have 2 angles, theta and phi. So if we were to draw out a coordinate system, just to show you what theta and phi are, so we have our 3-dimensional coordinate system. Phi is going around in this direction and goes from 0 to 2 pi, and theta is going in this direction from positive z to negative z and goes from 0 to pi, just to kind of give you an idea of what these 2 angles are showing. Now, for rotation, there is no forces opposing the rotation, so our potential energy term is 0 for rotation. Okay, so how do we go about solving this problem? And we're not going to go through the whole solving of the differential equation. We're going to go through the first couple of steps because we can see some important points that will influence our solutions here. The first thing we're going to do is multiply both sides of the equation by this constant and then group all of our constant terms together. So we're going to group in 2 mu r naught squared times the energy divided by h bar squared. And we're going to group this in one term, beta, just like we had before. So we're grouping all of our various terms together. And to remind you of what these variables are, mu is the reduced mass because we have 2 masses that are rotating, and then r naught is the equilibrium bond length. And energy is, of course, the energy. And now what we're going to do is multiply both sides of the equation after we do that by this sine squared over theta, which removes that from the denominator. And then we're going to switch the location of this term and this term. And that's going to give us some important insights about the nature of this problem. So after we do that, we end up with the following expression. We have sine theta times the partial derivative with respect to theta of sine theta times the partial derivative with respect to theta of our functions y of theta and phi plus beta sine squared theta times our function y of theta and phi is now equal to the minus second partial derivative with respect to phi of our functions y of theta and phi. Okay, so now that we're at this stage, we can note something about this problem. So we have 2 differential equations on each side of the equation, and they're different. They're all wholly reliable on one variable. So this side, the differential equations are only with respect to theta, and the other side, they're only with respect to phi. So from this, we can extract a couple of useful pieces of information. One, we have to be able to break apart our function. So our function y of theta and phi, we can deconstruct the variables. So we actually have 2 functions, one that's only a function of theta, and one that's only a function of phi, because of the way this differential equation is broken down. And the next thing we can do is say that both sides of these equations, for them to be equal to each other, we can't take 2 derivatives of a function of phi and end up with any phi terms in there that weren't in the original. So our 2 functions here have to equal a constant, and both sides, and that's going to help us solve this differential equation. So we can further break this down. So what we're going to do is take this term and substitute it in for every y theta and phi. And then when we're taking the partial derivative with respect to theta, we can pull out the phi term, and then likewise for the other way around. And so what that ends up getting us is the following. So we have 1 over our function of theta times sine theta times d theta. And now notice that since we're no longer considering partial derivatives, we removed all of the thetas from one side of our equation. We remove the partial derivatives and just have a regular old derivative times our derivative of our function theta, and then plus beta sine squared theta is equal to minus 1 over our function of phi times 2 derivatives with respect to phi of our function of phi. So what we've done is, again, just substituted in a function of theta and phi for our y functions, and then we divided both sides of the equation by our functions of theta and phi. Okay, so these are the differential equations we need to solve, and recognizing that they both equal a constant. And then we can put them back together to get our final solutions. So what we'll see, I write it up here, is that our solutions will be dependent on two quantum numbers, L and M sub L. We'll talk about them at the end. And our theta functions will be dependent on both of these quantum numbers. And our phi functions will only be dependent on the M sub L quantum number. And okay, so what are these solutions? Well, the solution to this differential equation, where this is equal to a constant, is something that we've actually seen before. So our functions of phi that depend on ML are simply equal to e to the I ML phi. So that one is pretty straightforward. Now the other differential equation is not pretty straightforward, and that's okay. So we'll just provide the solutions to that. So just like we saw for our harmonic oscillator, our functions of phi are a little bit more complicated. I'll write down what they are for your information. You don't need to know what they are. But there's this oscillating -1 term out in the front. Then we have a normalization constant here that takes the form of 2L minus 1, the square root of 2L minus 1 times L minus ML factorial over 4 pi times L plus ML factorial. That's going to normalize our equation. And then we have another polynomials here. So our polynomial depending on both L and ML. And like before, where we saw that our polynomial was dependent on the square root of alpha times x, here our polynomial is a function of cosine theta, which gives us lots of different angles. And this is a relatively complicated polynomial. I'll go ahead and show you what it is here. So this, as a function of x, this polynomial is -1 to the ML over 2L L factorial times 1 minus x squared to the ML over 2. And then we take derivatives based on L and M sub L. Take that many derivatives, as many derivatives as the sum of them, of x squared minus 1 to the L. Okay, so again, you don't have to do any of this unless you're really interested to like find out what the orbitals are, but I'll provide the first few of these orbitals here. So our functions, so we can go y is 0, 0 if L and ML are 0. So this would have no phi term if ML was 0. And there's also actually no y term if ML is 0. It's simply 1 over the square root of 4 pi. And then we can keep going. So if we had y 1, 0 as a function of theta and phi, now we'd have a polynomial term. We end up with the square root of 3 over 4 pi times cosine theta. And then we can do y1 plus or minus 1. And that's going to give us the square root of 3 over 8 pi times sine theta. And now we have finally a phi term. So e to the plus or minus I ML phi, depending on whether or not we use ML as plus or minus 1. So you can see there are some restrictions in here built into L and ML, and you kind of know what these are, and I'll justify that at the end as well. All right, so here we have the eigenfunction solutions, but what are the energy levels? If we wanted to calculate them, we could simply plug these equations back into the Schrodinger equation and solve. I'm going to provide them for you, however. So the energy levels only depend on L, and they are equal to h bar squared over 2I times L plus 1, where here our mu r naught squared has been combined into I, the moment of inertia. So that's what I is. All right, before we move on to talking about what these quantum numbers are and other commuting operators, I want to point out that we can combine these equations in different ways to remove this. So if we wanted to say plot these functions, it's kind of hard to plot functions that have imaginary numbers because they're not real. So what we can do is combine these. We can take linear combinations of these functions to remove the I term. So how do we do that? Well, I'll show you down here. So for example, we can take 1 over the square root of 2, and that's going to ensure that our new orbital is 1/2 of each of the old orbitals. And we can multiply them here. So we go y 1, 1, and then we'll add y 1 minus 1. And what is that going to get us? So I'll pull out the constants up here that aren't changing when we take the linear combination. And that's going to be the square root of 3 over 8 pi. So we'll multiply that by the square root of 2. So we'll have the square root of 3 over 16 pi sine theta. And now what's changing as we have 1 and minus 1 is the exponent. So we'll have this is multiplied by e to the IML phi plus e to the minus IML phi. Okay, so what does this get us? Well, what we're going to need to do is use Euler's formula to break apart these exponent terms into their sine and cosine terms. So this is going to give us a square root of 3 over 16 pi sine theta. And then we'll have in here, e to the IML phi becomes cosine of ML. Well, sorry, I shouldn't have ML in here. ML is 1. So we have e to the I phi, e to the minus I phi. So cosine of phi plus I sine phi. And then this term here becomes plus cosine phi minus I sine phi. So you can see here our two terms with I will cancel, and we'll end up with 2 cosine phi on the inside. So substituting that back in, we'll end up with the square root of 3 over 4 pi sine theta cosine phi. And this has removed our imaginary number. This function is still an eigenfunction of the total energy operator. It's still orthogonal with all the other eigenfunctions. It's just a combination of these two orbitals here that remove the imaginary numbers. Okay, so the last thing I want to talk about is what our quantum numbers are getting at here. What do our L and our M sub L mean? And to do that, we're going to look at the energy here. So the energy we've shown, or we didn't show, but I told you, and you could show if you wanted, that energy is equal to h bar squared over 2I times L plus 1. But for rotation in general, the energy is also equal to L squared over 2I. And what is this? Well, L squared is simply the angular momentum. And this is a direct comparison to our normal energy. So you might not know how energy relates to linear momentum, but you know in the linear world that energy is equal to 1/2 mv squared. You could also convert this into p squared over 2m if you wanted. So you can see there's a direct analogy here. We've changed our mass into our moment of inertia, but we still have this momentum squared over 2 times this mass-related term. So our energy is equal to L squared over 2I. So the only difference between the total energy operator, so if we were to operate with the total energy operator, the Hamiltonian, on our wave functions, what we would get is h bar squared over 2I L plus 1 times our wave functions again. That's what it means for this to be the energy. When you operate on it with our corresponding operator, you return the function multiplied by its energy, or by the constant that's the energy. So the only difference between this total energy operator and, say, an L squared operator is this over 2I. So that means that there's this L squared operator that when we operate on our spherical harmonic functions, they commute because they only differ by a constant, and we should get h bar squared L plus 1 times our function again. So this L squared operator is going to commute with the total energy operator, and it also is going to give us our linear momentum. So when we use the L squared operator, we don't get, not our linear momentum, sorry, our angular momentum. When we operate with the L squared operator, we don't get directly our angular momentum. We actually get the square of our angular momentum, which will tell us the magnitude of our angular momentum. So when we do this, we end up getting that L squared is equal to h bar squared times L plus 1. So if we want to know what the linear or the angular momentum is, we take the square root of that. And that only gives us the magnitude. We lose the vector components of that, but we know that the magnitude is h bar times the square root of L plus 1. Last, we have another operator that's going to commute. So if we scroll up here, we'll see that our functions in general are functions of theta and phi. And our phi functions are simply e to the I ml phi. And so there's another operator, the LZ operator, that only takes a derivative with respect to phi. So if we take a derivative of this function with respect to just our phi here, we're going to see that we're going to end up not changing the function overall. So our function is going to commute. So we also have an LZ operator that when we operate on our YL M sub L functions, we end up returning h bar times M sub L, and then times our function y of ML. So here our functions are these functions are also eigenfunctions of this LZ operator. And so this is going to tell us the z component of the angular momentum. So here our L squared operator commutes with the total energy and gives us the magnitude of our angular momentum. And this also commutes and gives us the z component of the angular momentum. And the other two directions don't commute. So we can't know the x and y components. We can only know one component, which we take to be in the z direction, and the magnitude, according to Heisenberg's uncertainty principle. Now, if we consider L and M sub L in this way, so here you can see L is determining, or here you can see L is determining the magnitude of the angular momentum, and M sub L is the z component, we can see how they are related. So for example, if we take L is equal to 2, we plug this in and we get that the magnitude of the angular momentum vector is equal to h bar times the square root of 6, which is about 2.45. So if the magnitude of our angular momentum is about 2.5, we can see that the z component, which is quantized, can't be more than 2, because if our z component was 3 and our total length was less than 3, that doesn't make any sense. So here we can see a restriction of our M sub L based on what L is. And so if we think about this, we can think about our molecule rotating. And so we may say here, maybe this is our L, this is our 2.45, and we could think about this being in different directions here. But the length always has to be the same. So the magnitude always has to be the same. And what this is going to give us, if I did a OK drawing, is at every point here, we are dropping by M sub L. So here our H bar is equal to, our L is equal to 2.45 H bar, and here our M sub L is equal to just H bar. And so you can see there are only certain rotations, M sub Ls that are allowed based on these vector components. All right, so to conclude this video, we showed some of the steps involved in solving the Schrodinger equation for the rigid rotor. It's dependent on 2 quantum numbers because it's a 2-dimensional problem. So its rotation is in 3 dimensions, but we've restricted the bond length, so we only have 2 dimensions that are changing. There are a couple of operators that commute with the total energy operator, namely L squared and LZ. These give us the meaning behind our L and M sub L quantum numbers, where L isn't quite, but it gives us the magnitude of our angular momentum vector, and M sub L is one of those components. And that gives us this interrelationship where M sub L is equal to plus or minus L, and then plus or minus L minus 1, and then all the way down to 0.